the ref parse of the root tree. You can ignore the funny notation there. What's important is I managed to get the hash of the tree object, which is again a SHA-1 hash. And it's important, once you have the SHA-1 hash, you can pretty much retrieve anything. You can just look in the objects folder and you'll get it. And I have run LS-tree, which is a human readable version of what the tree looks like. So this is all a tree is. It's just a listing of files and folders, or more specifically blobs in trees. And you can see a tree can either contain a blob or other trees. But note that these are just keys. These aren't actually containing the content. So if I want to retrieve the make file, I would have to still ask the get object store, what's the make file like, and give the blob using my get blob script. So it's still a flat structure in the database. Let's talk about commits. So this is the last bit that completes what structurally things look like. Actually, there's a bit more, but I'll get to that. So again, ignore the git ref parse head. It's again a command that will let me get the hash for my commit object. So this is what a commit looks like, and this is how I retrieve it using the Python code. If you noticed, the code to get a blob and a commit object is exactly the same. I open the file using the hash I have, I decompress it with zlib, and I just print it out. And a commit object is literally that, right? You can have, it's like a text file. It says commit followed by the number of bytes to know what kind of an object it is and how big it is. And it has some information that says commit followed by a number, tree followed by a number on the first line, and some author information, and below that, that's the commit message that you supply to Git when you're committing. So the parent is actually the parent commit, as you can see in the picture there, and that's like the commit before this. So if this was your very first commit, you won't have a parent. And you have a tree. So if I have the handle to any commit hash, I can actually access any tree and hence any file and any previous version as well. I have the full view of what the repository is like and what it could be at any point of time. So now the next bit is, how do I remember all these hashes? It's a hassle, right? Who's going to remember these numbers? I'm not going to know that 2 versions ago the hash was this. So you have the next bit, which is branches. Branches are actually, like a lot of people think, they are about like different ways of working, and they are in practice, where you might make a branch to build a feature. But they are also one of the only few mechanisms to know which hash to work on. And branches are pointers to commits. I hope that was clear. So your refs will be reset back to the state they were in. If you go back. More back. Keep going. Yeah, stop. Yeah. So you're saying if I do a reset from E to C, right? It'll just be the reverse of that. Play the slide backwards. So it will move that ref. So if I do reset from the main branch, it'll move main back by 1 step to C. And that's what your state looks like. Yeah, D is just gone. Yeah. I mean, it will be in your object store still, and I can access it because I have the ref log, but it's unreachable now.
Yeah, about the rebase part, there were 2 dangling commits, right?
Yeah.
So when does git clean this up? When do they do it?
Yeah, so there is this command called git gc. You can check the docs for it because there's a lot of parameters to it that I don't remember. But what it does is, it notices if, it runs every once in a while when you run a few commands. So usually that's a fetch, pull, any of those network commands that anyway take time, right? It'll also run a maintenance cycle which will see what all commits are unreachable. And it'll mark that as delete this as soon as in like 30 days or whatever. And you can configure all of these things, like you can configure when to do maintenance, how often you want to do it, and what the garbage collection cycle is like. Okay, are we good here? Okay, it seems to be no more questions. I'm around, by the way. You can ask me anything about Git, how the project works, what you want to what you want to understand about it. And I hope you're actually more confident using Git now that you know branches are pointers to commits. That helps a lot. And you would know what to look for and what these words mean, refs, heads, fetches, and things like that. Yeah, thanks.
Thank you, sir. I now call Fossil Secretary Abdul Latif to extend the memento to Atharva. I now invite the organizing committee head, Pavitra to extend the memento to Mr. Prabhanshu Gupta. Okay, thank you. Please note that lunch has been arranged in the lobby outside. And for those of you who have registered for workshops, you would have received a mail regarding the venues and the time. And if you haven't already registered, the registrations are still open at the registration desk outside. Thank you.
Case of Git merge is it? I talked about two different cases. Fast forward merge, right? That's exactly what's happening. It has advanced a main branch to fetch head. So a git pull is just a git fetch followed by git merge it with fetch head. Merge it with the fetch head thing. And that's how you have reached to the same state as your remote. Now you'll see a remote and this is on the same state and your branch is on the same branch that you've pulled from in remote. Now a little bit of a break between all this network stuff. I want to talk about git diffs. So that is what you can think of the line by line changes. Again, the one that Subin was talking about, which are these deltas. It's not too clear in this diagram, but they are two text files. And the green bit on the third line is someone adding a new file between two different change sets, which in Git parlance is commit. So if you apply, so there's this property that comes with these diffs. So you'll notice it has a bunch of other information on top. I'm going to read it out. One is the name of the A side and B side, which are the two files we are diffing, finding the difference between. And it'll give you two hashes. So those are the hashes of the blobs that correspond to these two versions, and we are finding the diff between them. And it also gives some other information about the line number in the file where this change happens. So I'm saying this change happens between line, even I can't read this that well, line 2 to 5. And you have like the plus and minus to say what's changed. So here's the thing, if I take a file and I take all of this information, I get an operation called apply, where I can just paste this on any random file and I'll be able to get to a new file. And this is often used a lot when you're trying to merge things and get things, right? It'll merge things using the diffs calculated between the common base commit that you have between your diverged branches and apply them. Okay, let's talk about rebase. And rebase is dreaded by a lot of people. It's very confusing. But I think if you have understood merge this way, you'll realize rebase is no big deal. It's not very different, it's quite simple actually. So you have A, B, E, F, those are commit hashes for the main branch. And you have a branch from C and D, starting from B, called feature X, and we are on the feature X branch this time. And what we are trying to do here is replay commits on a new base commit. So that's what happens when you run git rebase main. It says, take the commit object C and D and replay it on top of a new base, and our new base is main. So we can replace C and D on top of F. That's what. So when you run git add, it will turn your files into blobs and put them in the index. So that's telling Git, hey, this file is part of the version control now. And unless you don't tell it that, Git wouldn't know it has to version control this file. And after you do that, it'll subsequently be able to calculate whether something has changed since your previous commit or not, because it looks up the index and uses the index to figure a lot of these operations out. And yeah, when you commit it, it will take these state changes saying, hey, can you please add this to the next commit and make it into a commit object. Okay, let's put it all together. It's a big diagram, and I think not all parts of it is clear on this screen, but I will explain the important bits. So you have the working copy, which is everything outside the Git folder. That's what you're actually working on. You have the index, and the index can point to files that are already in your Git repository store, or they may not even be that, right? Like if it's a new file, it would just be on its own and not linked to by any other tree or any other commit. And on top we have head in feature X on the top right, and those are branches. I'm not using the technically correct term. The technically correct term is ref. So a ref is actually anything that points to a commit object, and head is actually a pseudo ref which points to any ref. And head is just a special kind of branch that says, this is what I want my working directory to look like. I want it to look like whatever the snapshot is for feature X, which points to this commit object. So you'll also notice there's a lot of structural sharing going around. So every time you make a new commit, you don't have to make a new copy of a blob every time. You can just point to whatever it was earlier if it has not changed since the last commit. So it'll save some space. Okay. So quick summary. I've gone quite quickly, and I'll definitely pause for a midway set of questions and repeat anything. But here are a bunch of questions. Do we store a copy of the entire code for every version of the repository? So what I'm saying is, if I have a file, a readme file, I commit it once, and then I commit it again, is it actually storing another copy of the readme file? So if I have 100 commits, am I having 100 separate compressed files? What do you think? Anyone?
No. It just tracks the line.
Okay. Sorry, what's your name? Subin. Yeah, Subin says it tracks the line. So it's sort of like tracking only the diffs, the changes. And you can go to the next slide. That's not exactly true. It's actually storing more. So CND are dangling, and they will eventually be garbage collected. But that takes a long time. The default setting for garbage collection, I don't remember, it's like in the scale of days. And that's assuming you lost it from your ref log, which, that's just around for quite a bit as well. So you don't really lose those changes. You've just changed this up. Okay, we can move on. Yeah, there's some downsides to Git's architecture. One is Git is really problematic for really large monorepos. And by really large, I mean really, really large. So if we know the Linux kernel is hosted on Git, and that was what Git was made for. It was actually made by Linus Torvalds in like the span of like 1.5 months, because he was fed up of proprietary version control solutions that existed back then, and the open source ones were also pretty bad to him, and for the case of Linux kernel. Yeah, and then he passed it on to another maintainer shortly after. But when you're talking about Microsoft scale, right, where a lot of these companies have large monorepos, I believe, and they put all of their big projects, everything, like the whole company in this one folder under Git. If you do that, you're in trouble, because as you saw at Git index, it's a flat structure which lists all the files. So once you're going to like millions, 100 million files, right? Every time I do a Git status, I have to go through all those files, calculate the diffs between whatever you're diffing against, and that's really slow. There are some solutions built for this. So I'd say most of the Git development that goes these days, or like a lot of the big features, are trying to solve this problem, which is how do you make it work with these large monorepos. And the contributors are often from Google and Microsoft, and they've built things like sparse index, which is like a more optimized index for these large monorepos. Since we are repeating everything, and that's quite important to know why Git is fast. It's because of this. Okay, we can go back to that slide. So the second question is, I think, immediately answered based on my discussion. Do we only store the difference between previous and next version and replay it when we need them? This was true in a lot of old version control systems, but it's not true in Git. No. Yeah, that's a simple no. That's not really true in Git, and the reason for that is performance and speed. And a lot of the old version control systems like RCS actually did that because storage was expensive. Do we store the information in a special database? By special database, like, think of like Postgres or something. It has its own way of seeing the data and being able to retrieve it. What do you think? Any answers? Any takers?
No.
No. Yeah, that's right. That's no is the answer. We just use the file system, as you've just seen. I can literally open it by using a Python script and get any blob, any tree, anything that Git knows. I can get it by just using the file system open call. Okay, let's move on. I'm going to take a pause here for 3 minutes, and any questions, anything that you felt was worth repeating? Or any questions about Git objects and how it's stored? Alright, so I'm taking it as it's been clear so far. Is it clear so far? No confusion? Okay. Yes, the one where I am taking the header and content and appending it. Yeah, can you go a few slides behind? A little more behind. I think the other one had much bigger text. Yeah, this slide, right? Okay, yeah, I'll let you sink this in a bit. I think I didn't give a lot of time to let this sink in, but I'm opening a file name, so this might be readme.md, and then I'm reading the contents of the file, which just say how to set up your repository, and I create a header, which is blob plus length of content, and then I'm creating a key. Again, this is important to know that you have a key which lets you access things in the repository. Yeah, almost like Redis, right? Like you need the key to get the data, and so the data is again separately stored. That's your zlib compressed file, and everything is flagged. So I know the hash, I'll get the object. Yeah, so that's what's going on there. All right, let's talk about branching, merge and rebase. And these are the bits that trip a lot of people up. But I hope it'll make sense now that I've given you a background of what a Git repository looks like. You just have a bunch of commit objects and pointers to these commit objects. So branches are nothing more than that. They're just pointers to these objects. So yeah, let's move on. Refs. I did mention this already. They are pointers to commit objects. And you have branching, which is implemented via these refs. Again, we read the ref file, remember. When we asked head what it is, it said it's refs head master. Say if I do a git checkout to something that's not master, it would say refs heads feature X. So that's telling you what we are pointing to right now. And in that previous diagram, the putting it all together big diagram, those were all refs. So your refs might look like feature X, head, main, origin / whatever, right? These are all refs. And they're mutable, as in we can change what a ref points to. But objects are immutable. What does that mean? So if I go back to a commit object, we delete it, only the unreachable. So if I follow a ref and trace through everything, and if I still can't reach your commit object, then it can be garbage collected by Git, and this is similar to what you think of in other languages, right? It looks for something that cannot be reached and frees it up. In Git, it just says delete this. And one last point, it's not present in the ref log. So I'll just quickly mention what a ref log is. It's basically this ledger that keeps a track every time you switch branches. So if I switch from main to feature X, it'll say it's switched from the commit object of this hash to the other hash. So in a sense, even if I lose track of everything, it's there in the ref log. I can get the hash and retrieve content that is unreachable because the ref log knows about it. So we are saying if we run out of ref log, like the ref log has a certain limit of how many such records are there, then it is actually possible to lose your changes, but that's really hard to do. Like, you'd be surprised how hard it is to lose your changes once you've committed it. Yeah. So I'm going to talk about merging and how that mechanism works. So this is a local merge. I'm merging a branch that's in my local repository with another branch in my local repository. So that's the main branch. And notice head is on main branch. So it means we are checked out on the main branch. Our working directory looks like what's in the main branch. And someone's opened a feature X branch. And I run git merge feature X. So that means merge with changes in feature X into our branch. And hit next. Let's see what that looks like. So you notice one is the main branch is advanced to a new commit object, E. So assume A, B, C, D, E are all hashes. So I've created a new hash here. And we are advanced to that new hash. And E has two parents. So remember the commit object line that said parent and hash name? We have two of those lines. And one of the parents is C and one of the parents is D. And our feature X branch remains where it is. So this is what happens when you run a git merge. It sees the changes that have been made between B and C and B and D and puts them all together and creates a new commit with both the changes. And conflicts may happen, but I can get into that a different time about how that mechanism works. It usually has to be resolved by you. Now we will talk about a special case of a merge, and this is quite important when you want to know what the hell is happening when I run a git pull. And that's a fast forward merge. So you have a main branch here, and that's on B, and you have a feature X branch here. So notice the difference from last time. We don't have a diverged feature branch, right? Your feature branch is just a superset of the main branch. So when I run git merge feature X, the same command as before. You can go next. A new commit object is not created here. It's just advance the branch ahead because it can, right? Like that is the merge. There is no extra code coming from main. So since I could just advance it, Git makes this optimization for you. And it says it's a fast forward merge. Next time when you pull changes from upstream, notice that Git will say merge has been fast forwarded. That's what this means. It means it didn't have to create a new commit object because you are running a subset of what the remote branch had. Now let's talk about the remote side of things. Git fetch git pull. So this is git fetch, and on the top I have my origin repo, which is often on GitHub. It need not be, by the way. It need not even be a company. It can be just another computer, and that's actually the spirit of decentralized version control. But that's a talk for another time. And we have a local repository here, and I run git fetch origin. And what this tells me is, hey server, I want to match up with what you have. Can you give me all the missing objects, the objects that I don't have? So the objects that I don't have in this diagram is the commit object C and everything else that I might not have that came in as a part of C. So all the trees, all the blobs, everything. And you can hit next. So it sends this over the network, and a function that takes a number and gives you another number. It's quite hard to reverse the process. So the SHA-1 hash is the key of this database. So if I ask for this key, I would get a value, which is a git object. In the most common case, or the most important case, it's a zlib compressed file. So zlib is the software that will just compress your files, make it smaller by encoding it. And branches are pointers to commit objects. I'm going to say that word a lot. It's really important. Branches are commits. Branches are not commits. Branches are pointers to commit objects. So yeah, let's move on. So this is the Git database. When I run a Git init, you will see a folder called .git, and that's where all the Git information lies. Everything outside it is just your directory, just your project as it always is. That's what you would call your working directory. And we have three types of Git objects: a blob, a tree, and a commit. So a blob is a zlib compressed binary file. These are often the files you're working on, your readme files, your code files. There are a bunch of other files that are not blobs, that are zlib compressed. We'll get to them. We also have a tree and commit. So tree contains metadata about blobs and trees. It lets you group things. So maybe I have a root tree that corresponds to the root directory, and I'll contain a bunch of blobs and other trees. So that's, if I have the access to a tree, I'll have the access to all the keys that will let me get the other things. And you have the commit objects, which you're most familiar with. That's where you put your commit message, contains information about the author and stuff, and it points to your root tree, and it'll let you even get to the previous commit. So you essentially have snapshots that you can move between, and that's where the version control aspect comes in. So let's talk about blobs. Move on. So here's how you make a blob. You notice I've not used any git commands yet, and you'll be surprised by how few there are in this talk. So this is just a Python script I wrote that lets you create a blob if you want to by hand. And I'll just explain the important bits. There's a content and a header, and the content is actually a file. So if I want to commit my readme file, that would be the content, and you have the header, which just says SHA-1 of header plus content. The header is just saying blob followed by the length of the content and a null byte. So if I have like a 300 byte file, it would be blob 300. And you put them together, you create the blob key by running the SHA-1 algorithm on it. And you have the value, which is the zlib compressed content. And you just save it in your .git objects folder. So I'm saving it in .git/objects. The first two letters or characters of your key is the first folder, so it's kind of bucketed based on the first two characters, and the rest. There are different reasons why this was made. It's more of a consequence of history. Yeah.
A follow-up question to that, like SQLite DBs are really fast locally. So instead of using this whole file system architecture, they could have just gone with a DB, like how SQL is using it. So
sorry, how?
SVM, Subversion is also using a DB.
Right. For that. So by the way, you mentioned SQLite. There's actually a very interesting alternative to Git called Fossil, and it's by the creator of SQLite, and he's used that as the DB. Yeah, that's definitely an option, but I'm not too sure. I don't exactly remember why they went with a file system architecture. Usually, a lot of the design decisions were driven by a few things. One is, I think they have a common like refrain, which is don't do what CVS is doing, and SVN is based on CVS. And the other is it should work for the Linux kernel. So I think with, like I guess you could say that this is not really a excellent fit for a relational model, although I do agree SQLite works well, and you have Fossil as an example of that. Yeah, sorry, I don't have a very good answer as to why it's purely on a file system. I suppose it can be to do with not depending on as many things as possible. Just use what the operating system gives you.
It is also the Unix way. So in Unix, everything is a file. And
Yeah, perhaps. So, Abraham? Yeah, Abraham says it's probably because everything is a file. That might be a good explanation. Although, I think Torvalds is not that hardcore Unixy. Like, he's quite pragmatic. Sometimes he deviates from that rule. He's known to have done that, I think. But yeah.
Are there any, like, other than file system based Git backends? Like, I mean, something like GitHub must be having redundancy and not on the file system, right? I'm just assuming, I'm actually not sure.
So I would say no, it still uses the same file system calls that we have. So you have like your open syscall, but obviously the file system itself can be anything, right? It can be your what's on your laptop, the ext file system. It could be like a really fancy file system like ZFS or some kind of network file system. So if that's one way you can control what the backend is like, but it's still coming from the file system interface. Okay. Also, yeah, I'll be around for this conference till tomorrow. Yeah.
When you do rebase and merge,
On GitHub, it's like the merge part of it is more like you are closing the pull request, but you are closing the pull request and putting it in the main, not with the merge but with the rebase. It's just they present it in that way.
Okay, so it's actually just a rebase.
It's just a rebase.
Okay, thanks for the answer, by the way. It is, so to answer your question, it's just a rebase.
What is a merge commit then? Like how? I'll ask a follow-up after.
Yeah, okay. So a merge commit. So when we merge two diverged branches, it creates a new commit. And I'll just tell you what the contents of the text file are in that. So is that what you're looking for? Okay. So remember our contents at commit, file size, parent commit, and tree, right? So in the case of a merge commit, I believe there is no tree, right? Because there is a tree, but it points to like some tree that already existed before, because it is, actually sorry, I'll correct myself. It's not pointing to a tree that existed before, it will point to some tree that has the changes from both sides of your branch. And I'll have two parent lines. So I'll say parent is either E or C, like in that diagram. Maybe it'll be helpful to see that diagram. But you have a feature X branch, main branch. So you're pointing to two parents, and you have the commit message, and the default one that Git says is merge feature X into that. You can change it if you want, but often it's not. So it is an extra record that just says that we have two parents coming from this. So the usefulness of this is that you know it came from two different lineages, two different lines of work. And you don't get that with rebase, where it looks like you came from one line of work. And both have their uses. But often if you're working in a big project, say in Git itself, right? I made a bunch of commits, and the maintainer merges it into the main branch. And they realized whatever I wrote was garbage, it was broken, and Git is being destroyed everywhere in the world. So they can just roll back the merge commit, and they'll be able to identify in my series of commits on my lineage which one actually broke the build. So it makes bisect quite easy. And bisect is just a command that does binary search of all your commits and checks which one broke the build. And you can say what broke the build means. So that might be failing the tests, for example. Yeah.
Is it a special commit in any way? Can we do a reset to the previous?
What it does is instead of actually storing your image, it'll store some other key, and you can then ask some other server for that other key and it'll give you the version you want. So you're kind of moving that problem elsewhere. And you also have shallow clone, which is useful. So when I run a git clone, what normally happens is, it's like a git fetch, but fetch everything from the beginning, because I'm starting with nothing. And that can take a long time if your repository is really big. A shallow clone just says, get me the newest commit object. If I check out to somewhere older, then you fetch it on demand. That's what's going on there. Alright, and a bit of an epilogue. So that's all the technical stuff out of the way. And I did say the talk was about something a bit more than just Git, even though it's Git splits. Okay, let's move on. So the epilogue here is, beauty comes to those who seek it. And this is an image from the Git mailing list of someone who was really frustrated with Git, as we all have been at some point, and demanding that the maintainer of Git Junior, the person who took over after like 1 month of Linus working on it, he should step down. And all I want to say is, I think the issue here is the person has failed to see the beauty where it was. This architecture is really elegant, it's really performant, and it's decentralized. You don't have to reach for a server to actually view the status of what's going on, which I had to for my own presentation slides. Okay, let's go on. So this is just a quote by an Irish poet, and he says, when our eyes are graced with wonder, the world reveals its wonders to us. There are people who see only dullness in the world, and that's because their eyes have already been dulled. So much depends on how we look at things, and the quality of looking determines what we see. And why I bring this to a FOSS conference is, you can go next. Why I bring this to a FOSS conference is that free and open source software lets you appreciate this beauty. You can really go to the source code, open things up, and you can actually learn a lot. And I think this is really important, especially at a college level. And I feel like that has given me personally the most for my career, that I was able to just go to these things, learn on it, learn from it, because it's all out there for you to learn from. So just make the most of it. It's fun. And yeah, that's the end of my talk. And I'm open to questions. So I'll take any questions about Git, contributing to Git, because I've done a bit of that, and anything else about FOSS software engineering. It's the audience's time now.